Have you ever wondered when you write a line of code like print hello world, how does the computer understand what that means and turn it into something that actually runs on your screen? You might have heard people say things like, Python is an interpreted language, or C is a compiled language. But what does that really mean? Today, let's explore exactly how a program gets translated into something a computer can run. We'll lift the veil on compilers and interpreters and uncover how computers transform your code into action. First, let's get one thing clear. Computers only understand 0 and 1. That means any code you write, no matter what language you use, has to eventually be translated into machine code, which the CPU can understand and execute. But as humans, we write code in high-level languages like Python, C, or Java languages that are much closer to English than binary. So there's a big gap between what we write and what computers understand. To bridge that gap, we need a translator. And that translation happens in two main ways: compilers and interpreters. A compiler is a program that takes your entire source code and translates it all at once into machine code. It produces a standalone executable file like .exe on Windows or an ELF binary on Linux. From there, you can run the program directly with no need to translate it again. Think of it like hiring a translator to turn an entire novel into English, print it as a new book, and hand it to the reader. Once it's translated, the translator's job is done. The compilation process goes through several structured stages. Lexical analysis breaks your code into basic units called tokens. For example, A equals 1 plus 2 becomes A equals 1 plus 2. Syntax analysis checks the structure of your code, making sure it follows the rules of the language and builds an abstract syntax tree, AST. Semantic analysis ensures the logic makes sense. For example, it'll flag an error if you try to add a number to a string. Intermediate code generation transforms the AST into a platform-independent middle form of code. Optimization cleans up the code, removing inefficiencies like redundant calculations or simplifying loops. Target code generation converts the optimized code into machine code specific to your CPU architecture. The result is the machine code runs directly on the CPU, no retranslation needed. But if you change your code, you'll need to recompile it, and the compiled binary will only work on compatible hardware, for example, x86 versus ARM. An interpreter, on the other hand, doesn't produce a separate executable. Instead, it reads and translates your code line by line, executing it in real time. It's like having a live translator stand next to you, reading each sentence aloud and instantly translating it into another language as you go. The key steps for interpreters are lexical and syntax analysis, similar to compilers, but done per line or block. Immediate execution. Instead of generating machine code, the interpreter directly runs each piece of code using built-in logic. No output file. The program only runs while the interpreter is active. Once you close the interpreter, everything stops. This makes interpreters great for rapid development and debugging, since you can test changes without recompiling. But because each run involves retranslating everything, interpreters are usually slower than compiled programs. On the flip side, interpreted languages are often more portable, since the same code can run anywhere the interpreter is installed. Now, you might wonder, can we get the speed of compiled languages and the flexibility of interpreted ones? Yes, many modern languages use a hybrid model. They first compile your code into bytecode, then use a virtual machine to interpret or execute it. A great example is Java. Java code is first compiled using Javakin to bytecode, a low-level platform-independent format. This bytecode is then run by the Java Virtual Machine, JVM, which acts as a middleman between your code and the hardware. The JVM interprets the bytecode into machine code that the CPU can run. This approach allows Java to achieve its famous slogan, write once, run anywhere. As long as the target machine has a JVM, your bytecode can run. But interpreting bytecode line by line still has performance costs. To solve this, modern JVMs use something called just-in-time JIT compilation. JIT compilers monitor your program as it runs. When they detect hot code parts of the program that are used frequently, they compile that code into machine code on the fly and cache it. Next time that code runs, it uses the cached machine code instead of interpreting it again. This brings execution speed close to that of fully compiled programs. Over time, the longer your Java program runs, the faster it gets. This is why Java apps may start slow, but pick up performance as they go. Other languages like Python also support this hybrid model. For example, PyPy is a version of Python that uses JIT to boost performance. The JIT compiler strikes a balance between flexibility and performance. For non-hotspot code, it continues using interpretation, which keeps startup fast and memory usage low. But for hotspot code that runs frequently, it compiles it into native machine code, reaching speeds close to those of fully compiled languages. That's why Java programs may feel a bit slow when they first start up, but performance improves significantly over time as JIT compilation kicks in. Java's compile plus interpret hybrid model also enables cross-platform compatibility. Since bytecode is hardware independent, the same .class file can run on any system with a JVM. In contrast, languages like C compile code directly into machine code tied to a specific CPU architecture, making cross-platform execution difficult. Java avoids the inefficiency of interpreted languages that translate line by line during runtime, while also skipping the hassle of having to recompile programs for every platform like traditional compiled languages. Let's break it down with examples. Compiled languages includes C compiled using GCC, often used for systems programming. C++, compiled with G++, widely used in high-performance software. Go produces a static binary cross-platform with separate builds. Rust focuses on safety and speed system-level development. Fortran, classic compiled language, still used in scientific computing. Interpreted languages includes Python, interpreted by CPython, widely used in scripting and AI. JavaScript, interpreted by the browser, for example, V8 engine. PHP, interpreted on the server side for web backends. Ruby, clean syntax, interpreted for fast prototyping. Shell scripts, interpreted by Bash or similar shells. Perl, older scripting language, still interpreted. Hybrid languages includes Java compiled to bytecode, run on the JVM with JIT. C compiled to intermediate language, run on Nets VM. Kotlin compiles to JVM bytecode, JavaScript, or native code. Python, interpreted by default, but implementations like PyPy support G. Lua, interpreted by default, with optional GT for speed. Scala, compiles to Java bytecode, runs on JVM, supports J. More and more languages today blur the line between compiled and interpreted. The key question is no longer, is it compiled or interpreted? But rather, does it generate native machine code? Does it rely on a VM? And how does it optimize performance? Even interpreters today are highly optimized. For instance, JavaScript engines like V8, used in Chrome and Node.js, use GT compilation to run 3D games, video editors, and even server-side apps. So, in real-world development, the best language depends on the job, not just raw speed. So to sum up today's video, we looked at how computers translate your code from high-level languages to machine code, and the different paths that process can take. Compilers, interpreters, and hybrid models like Java and Python with G. If you found this explanation helpful, don't forget to like the video. We post deep but easy to understand computer science content every week. Curious to dive deeper into how the JVM or JIT really works? Drop a comment below. And don't forget to subscribe. We'll see you in the next one.